Okay, so what I wanted to do today was probably finish chapter 8. And if you remember, chapter 8 is on hypothesis testing. And we skipped 8.1 because that's like an introduction to hypothesis testing. So last time we jumped straight into 8.2 just so we could have an example to work with. And the example we worked last time, if you remember, was there was a claim made about a population proportion. And by the way, 8.2 is about testing claims about population proportions. And we looked at an example in my math lab where there was a claim made about a population proportion. Someone claimed that more than 20% of people that were given this particular drug would develop nausea. And we set up the claim is P is greater than 0.2. Instead of writing it as 20%, we wrote it as 0.2 as a proportion. And that's the alternative hypothesis because there's no equal sign in it. And then the null hypothesis would be that it's less than or equal to 0.2. But and that's the reason it's the null hypothesis because there's an equal sign in it. But we commonly just think of that as just being p equal to 0.2. We don't bother with the less than or equal to. But just remember the null hypothesis has an equal sign in it and the alternative does not. And the initial claim is that p is greater than 0.2. So in this case, the claim is attached to the alternative. Um, there are times when the claim could be attached to the null hypothesis. For instance, if I were to claim that p was less than or equal to 0.2, then that would be the null hypothesis, but that would also be the claim. But in this case, the claim was p was greater than 0.2, and that's the alternative, and p being less than or equal to 2 would be the null hypothesis, or 0.2 would be the null hypothesis. So anyway, this is the problem we looked at. So to test the claim, they sampled 221 people at random and gave them that drug, and 52 of them developed nausea, and so the sample proportion turned out to be 52 divided by 221, if you remember, was about 23.5% or 0.235 as a proportion. And so we did the traditional method and we did the p-value method. And when you run let's talk about the p-value method. When you go through the p-value method, you assume anytime you run a hypothesis test, you assume the null hypothesis is true. So there's an assumption that's made about what this p is, even though we don't know what it is. When you run the test, the hypothesis test, you assume that it's whatever the null hypothesis says. So in this case, we assume that p is equal to 0.2 when we run the hypothesis test, right? So under that assumption, we're trying to evaluate how far away the sample proportion is from the population proportion. So you would think if you sample from this population with p equal to 0.2, that your sample proportions would be close to 0.2 as well, right? Because after all, you're sampling from a population where 20% of them develop nausea. At least that's the assumption when we run the test. So you would expect your sample proportion to be close to 0.2. So ultimately, what we're trying to do is determine how close this sample proportion is to this assumption about the population proportion being 0.2. And the way we do that is we determine how far apart these two numbers are in terms of not their absolute difference, but their relative difference in terms of how many z scores they're away from each other, or how many standard deviations are away from each other. And that's what this formula does. So what we did is we said, okay, we take the difference between the sample proportion and the assumption about the population proportion, so 0.235 minus 0.2, and we saw that that's a absolute difference of 0.035. But then we want to turn this into how far apart they are in terms of a number of standard deviations. And so this is what a standard deviation is equal to. It's the square root of p times q divided by sample size. And of course, we calculated what this number was. It was really small. But ultimately, 0.035, which is the absolute difference between these two numbers, turns out to be about 1.3 standard deviations away. Well, 0.235 is 1.3 standard deviations away from 0.2, right? That's what it says. That's how far apart they are, not as an absolute difference. This is the absolute difference between the numbers. As a relative difference in terms of a number of standard deviations, the distance between these two numbers is 1.3 standard deviations. Okay, and so it's called our test statistic. If you are doing the p-value method, what you do from there is you find the area from the test statistic to the right of the test statistic. And the reason we're going to the right is because this is greater than sign. And so if you find the area trapped from the test statistic 1.30 up to infinity, we found it to be about 0.0968, and that was what we call the p-value. And then you compare the p-value to alpha significance level, which in this case was, I believe, 0.01. And since the p-value is greater than alpha, which it is, then you fail to reject the null hypothesis. So that was the conclusion. So we had a failure to reject the null, which is basically saying that it seems reasonable. Our assumption is not, it's plausible. We're not saying that it's true. Our assumption, we're not saying there's evidence to say that it's equal to 0.2. We're just saying that that is a plausible possibility. That's the reason we can't reject it as a possibility. And if you can't reject the null hypothesis, then you can't support the alternative hypothesis, which is claim. So a conclusion here was that there's not enough evidence to support the claim using the p-value method. Now, you could also do it using the traditional method. Notice that the p-value method is a comparison between area above the test statistic and this area here, which is called alpha, the area in the tails. And if you do the traditional method, before you I shouldn't have erased the p-value method. We'll go back and look at it. But before you do anything, you find the critical value. And so what you do is you take this area that's in the tails, and in this case, there's only one tail. So it's a right-tailed test with total area in the tails being alpha, right? There's only one tail, so this tail should have 0.01. And so you have to look up the z-score, whose area to the right of it is 0.01, and it turned out to be 2.33, and that's called a critical value. And that's kind of a boundary that we use to determine whether we're going to reject the null hypothesis or fail to reject the null hypothesis. And if you do the traditional method, then you look at, you still find the test statistic, compare that to the critical value. And if the test statistic lands in this, what's called a critical region, then you reject the null. If it does not land in the critical region, which is what's happening here, then you fail to reject the null. So notice you get the same result as you did with the p-value method. So either way you do it, you end up with the same result. You fail to reject the null, and that means there's not enough evidence to support the claim. So regardless of which way you do it, that's the result. Again, I erased the p-value, but I'll go back and look it up. So the only difference again between the p-value method and the traditional method is a comparison between the two z-scores here. I mean, there's one z-score for the area to the right of alpha, and that's the boundary, 2.33, called the critical value. And then there's another z-score, which is called the test statistic, and the area to the right of it is called the p-value. So you can compare the two areas. If you're comparing the two areas, the p-value to the alpha, then that's called the p-value method. If you're comparing the two z-scores where those areas occur, then you're doing the traditional method. But you're going to get the same answer either way. So that's what we did last time. The reason I'm going back over this again is because you can also do this on the calculator, which I forgot to mention last time. So let's pick up there, and I want to show you. So if you do this on the calculator, you can go to Stat, I'm sorry, you can go to distribution. No, I'm sorry, stat. Sorry, it is under stat. And then scroll over to tests. And this is where we have, when we did confidence intervals, we looked for the word interval for confidence intervals, but now we're doing hypothesis tests. So we're looking for something that says test. And in this case, it is a test about a proportion. So you're looking for prop for proportion, and we're working with one population. And so if you look down here, you've got one prop z-test. That's exactly what we have. We have one population. We're working with a proportion, which turns into a bunch of z-scores, and it's a hypothesis test. So that's the one we want. And they label this a little differently than we might do it in our book. But the first thing they have is p sub 0. Now, their p sub 0 refers to this p here. They're labeling this sub 0. So it's the proportion, the population proportion, you're assuming, assumption about the population proportion based upon the null hypothesis. So they put a sub 0 for that. So whatever the null hypothesis, the assumption, you're assuming the null hypothesis is true. Whatever the p is for that assumption, they're labeling it with a sub 0, okay? Which is different than what we do. We don't do that in our book. So this would be whatever you're assuming p to be based upon the null hypothesis. So we assumed p was 0.2. X is, we sampled 221, and then I guess 52 of them developed nausea, so that's the number of successes. So that's X. I'm sorry, I got backwards. X is 52, N is 221. All right, and then this can be a little confusing because again, they're using different notation than we're using. First thing it says is proportion. So that refers to the population proportion. And you've got three options. It's not equal to p0, it's less than p sub 0, or greater than p sub 0. So this is what the alternative hypothesis is. So if you go look at the alternative hypothesis, this is the portion. They're calling this proportion. And then on this side, they're calling this p sub 0, which is 0.2. So when you see prop greater than p sub 0, not equal to p sub 0, or less than p sub 0, it's basically what this alternative hypothesis is showing us. So we have proportion under the alternative hypothesis. The proportion is, alternative hypothesis is that the proportion is greater than 0.2, which is what p sub 0 is. So this says p is greater than 0.2 if you read it that way. So they just use different notation. You got to get used to it. All right, and then that's what we have, right? Greater than, and then calculate. And you can see the z-score, 1.31, that's your test statistic. And then your p-value is 0.0948, which is, I think, what I had before. And then the test statistic here is not exactly the same, but that's probably because I rounded off here. Apparently this rounds off to 1.13 or 1.31. So you're getting the same answers from the calculator. And then notice the p-hat value right here. That is your sample proportion. And then they give you the sample size, 221. Okay, so it's a little bit nicer, but you should be able to This is the formula. And I showed you last time how to plug in all these numbers, and this is what the calculator is doing for us, right? It's basically using this formula to get the test statistic. And then once it gets the test statistic, it is finding the area from the test statistic on up to get the p-value. So anyway, I just wanted to mention that from last time. I wish I had remembered it last time, because I hate the fact that we went over this problem last time, but we didn't talk about how to do it on the calculator using the test functions on the calculator. But anyway, that was that was 8.2. This is a problem from 8.2. So what I really wanted to do today was talk about 8.3 and then possibly 8.4. So let's talk about that. 8.3, again, we're going to still be doing hypothesis testing. But this time we're going to be testing claims about population means instead of population proportions. So as an example, let me just pull one up from the homework. So this one says a data set about speed dating includes like ratings of male dates by their female dates. And so the summary statistics are they surveyed 186 female, I guess they surveyed 186 females about their male dates, and the average rating of their male dates was 7.81, right? That's your X bar, your sample mean. And the sample standard deviation S was 2.02. Okay, and so they want us to use a 0.05 significance level to test the claim that the population mean of such ratings is less than 8. And so they say assume that a simple random sample has been selected, so it's random sample. And then we're supposed to identify the null and alternative hypothesis, the test statistic, the p-value, and state the final conclusion about the original claim. Okay, so first thing is let's kind of outline what's going on here. So the population would consist of all presumably all dates where females would rate their male dates, right? So this would be all dates. I mean, it's just unimaginably big. And then you look at the ratings, average rating that female would have about the male date. You would average all those up, and that would be your population mean, which we call mu. Now, we will never know this number, right? Too many people, too many dates to even know what that number would be. Okay, so there's also the population standard deviation, which typically we wouldn't know either. But let's stay with the case where we might know this for some reason. Okay, let's say this is known. This problem, I don't think it's known. There's a possibility that population standard deviation is known. And there's a reason I want to talk about that in a second. Okay, so when you do a hypothesis test, the first thing you want to do is identify the claim. It's always the first step. So if you read through here, it says use a 0.05 significance level to test the claim that the population mean of such ratings is less than 8. So what they're claiming is that this mu, population mean, right, which we symbolize with the mu, claiming that it's less than 8. So there's the claim. And so then you have to decide, okay, is this the null hypothesis or the alternative? And of course, since it doesn't have an equal sign in it, it's the alternative hypothesis. And then the null hypothesis would be greater than or equal to 8, which of course has an equal sign in it. And a lot of times we just think of it as being equal to 8. So that's how this would set up. You should always start with the claim and write it down first, decide whether the claim is the alternative hypothesis or the null hypothesis. And of course, if it doesn't have an equal sign, it's the alternative. And if it does have the equal sign, then it's a claim. So I've mentioned this before. Claim could very well have been attached to the null hypothesis. If someone had claimed the average rating is greater than or equal to 8, then that would have been your claim, right? The null hypothesis. That's not what happened here. Claim was that it was strictly less than 8, so that's why it's the alternative hypothesis. So that's how it's set up. Now, let's do the traditional method first, and then we'll do the p-value method. Okay, so when you do the traditional method, the first thing you got to do is find the critical value, the boundary, before you run the test. Boundary that will decide whether you're going to reject or fail to reject the null, depending on which side you land on the boundary. And then you actually run the test and find the test statistic and see whether you land past the boundary or you land in front of the boundary. But before I do that, I want to mention one thing. Kind of underneath all this is an assumption that our X bar values are bell-shaped. So these are X values up here. The original population is that's the random variable X. Would be the rating of one individual female on a particular date. When you look at our sample, though, they sampled 186 women about their dates. And the average rating was 7.81 with a standard deviation of 2.02. Okay, so this is our sample data. When you start sampling several people, like 186, and averaging up the ratings, you're getting the X bar value, right? That's where that comes from. This is your random variable now, right? It's an average. X bar stands for the average rating. Up here, X stands for a single rating from a single person. Okay. And so they didn't tell us anything about the distribution of these X values up here. If you read through the problem. And we need the X bar values to be bell-shaped. So if you remember, there's two ways to get these X bar values to be bell-shaped. One is you need sample size to be above 30. If you're sampling more than 30, then these start to look bell-shaped. The other possibility is the X values are bell-shaped from the original population. So I don't think they told us that this was bell-shaped, right? We have no idea what the distribution here is. So the distribution here, I don't think they told us about the distribution of the original population of X values. We are sampling more than 186. So regardless of what this distribution looks like here, we know from the central limit theorem that if n is above 30, then these will start to look bell-shaped. So that's the reason the X bar values are bell-shaped. Just keep that in mind. Then what happens is we convert these over to either z-scores or t-scores, depending on the case that we're in. So if it's the case where sigma is known, if you remember, these would convert to z-scores. And the way you would convert an X bar value, right, these here, right, the X bar values here, to a z-score is you take the particular X bar value that you're trying to find the z-score for, you subtract off the average X bar value, which is called mu sub X bar. And if you remember, mu sub X bar is the same as mu sub X, this mu sub X here, which sometimes we just call mu. Sometimes we just call this sigma. But the means don't change, right? The mean of the X bar values is the same as the mean of the X values. And then after that, you divide by the standard deviation of the X bar values, which if you remember, is not the same as the standard deviation of the X values. They're not the same. This turns out to be the same as sigma sub X, this one, divided by the square root of the sample size. Now this is all coming from 6.4, right? So we talked about some of this in 6.4. That's how you convert an X bar value to a Z-score. But you can only do that if you know sigma sub X, right? If this is known. This is not realistic. If you think about it, if you don't know what the mean population mean is, then you're probably not going to know the population standard deviation, right? So it's not likely that you would know this. And by the way, once you convert these over, these Z-scores over here will remain bell-shaped. So whatever the distribution looks like over here, when you convert them to Z-scores, it has the same shape. And the middle here will convert to 0, a mean of 0. And so this is actually standard normal. Okay. But again, this requires us to know sigma sub X. All right, so let's take the realistic case. Let's say we don't know this. Which is more than likely what's going to happen. If you remember, what happens is if you know what we'd like to convert these to Z-scores, these X bar values to Z-scores, but if you don't know sigma sub X, you can't do that. So what do we do instead? We replace the sigma sub X with the sample standard deviation. So this is going to be replaced with S. But once you do that, it changes the distribution to a T distribution. And so these are now T scores, and this is a T distribution. And oh, by the way, you still need the X bar values to be bell-shaped. So you still need to think about how you're going to get that done. It still comes down to one of these two situations, right? Either you're sampling above 30, and that'll get them X bar values to be bell-shaped, which is what's happening here, or the original population of X values up here is bell-shaped. And that's not the situation here because we don't know the distribution of this population. They didn't tell us anything about it. So anyway, you still need the X bar values to be bell-shaped. But this time, the difference is they don't convert to Z-scores, they convert to T-scores because we're not plugging sigma sub X in here. We're substituting the sample standard deviation instead. Now, why do I mention that? Because this is going to be the test statistic. By the way, mu sub X bar is the same as mu sub X. So write it like this. And a lot of times we leave the subscript X off and we just write it as mu. Sometimes you'll just see this written as mu. But it really, it refers to this population mean here. Okay. It just so happens that they're the same. The mean of the X bar values is the same as the mean of the X values. Okay. So this is actually our test statistic. If sigma is not known, the realistic case. Now, if sigma is known, then you could use sigma here and you'll get a Z-score instead, right? But this is the realistic case. So anyway, you start with the X bar values being bell-shaped. You convert them to T-scores using this little formula. And the T-scores will have a T distribution now instead of a normal distribution. So I'm just going to draw that distribution and use that as our guide. Okay. All right. So then let's actually run the traditional method test. Okay. So we've set up hypothesis tests here, the null and the alternative. And now, first thing you do in the traditional method is you find the boundary, critical value, the boundary for your determining whether the null hypothesis is rejected or if you fail to reject it. All right, so remember, the way to do this is you look at the alternative hypothesis. So this has an arrow pointing to the left, so that means we have a left tail test. And then you want to look at your significance level. So in this particular case, we're testing at 0.05, right? 0.05 significance level. Remember, that's determined by the researcher or the statistician who's running the hypothesis test. So that's arbitrary. All right, but we're testing at 0.05. It's a left tail test. Remember alpha, the total area in the tails, and that's what the significance level is, right? So this is the total area in the tails. If we have two tails, we would divide it up evenly, but we only have one tail, right? We have a left tail. So that left tail has all of this area in it, okay, 0.05. And what we're going to do is we're going to find the t-score, not z-score, t-score, where this occurs. And obviously it's going to be a negative number, and that's going to be our critical value, our boundary. Okay, so if you're lucky, you'll have a calculator. If you go to the distribution button, if you're lucky, you'll have a calculator that'll have, just like inverse norm, it'll have an inverse t right below the TCDF. I have an older calculator, so it does not have inverse t on it. So if you don't have that, then you're going to have to use the t-table to do this. Okay, so I guess I'll just pull up a t-table from the internet. Okay, so for us, notice again at the top it has one tail or two tails. We have one tail. The amount of area in that one tail is 0.05. So 0.05 would be this column here. And then we have degrees of freedom now. So remember, degree of freedom is always one less than the sample size for a t-distribution. So for us, that would be 185. Now on the calculator, you do inverse t of the area to the left of the t-score that you're looking for. So you put 0.05 in, and then comma the degree of freedom, which would be 185. So you'd say inverse t of 0.05 with 185 degrees of freedom. If you don't have that, you're going to have to use the table, the t-table. All right, so I just got to scroll down to, let's see, this is the 1, 2, 3, 4, 5, 6th column. Okay, I'm going to scroll down. Okay, well, this table doesn't have all the values on it. The closest thing it has is 100. So 1, 2, 3, 4, 5, 6. It's about 1.660, but this is an estimate. Now, you can see it's not going to be that different because at 80, it's 1.664. At 185, it's going to be 1.66 something. Well, maybe 1.65. Because you can see it goes to 4.6 at 1,000, right? That's close enough. I mean, we don't need this to be perfectly accurate. Okay. So I'm just going to take 1.66. It's pretty close to that number. So that's going to be our critical value. Oh, by the way, table doesn't have negative numbers on it, right? So this assumes that you're talking about the t-score, the positive t-score on the right-hand side. So you just have to know that if you're on the left-hand side, that you have to turn it into a negative number. So for us, this is negative 1.66, okay? So to try to be clear about this, as clear as possible, table is giving you the t-score if the area to the right is 0.05. Okay. So this over here is 1.66. Yes, that's correct. But we're not looking for the one on the right. We're looking for the one on the left. The only difference between this one and this one is the fact that this one's negative 1.66. So you have to just know that if you're using the table. Now the calculator, when you do inverse t, the calculator will give you the negative number because you're putting in 0.05. Put in 0.95, the area to the left is 0.95, it'll give you positive 1.66. But if you put in 0.05, which is the area to the left, you'll get negative 1.66. Okay, so there's our boundary. And now let's run the test. Okay, so remember, the boundary is directly related to the significance level, which is the total area in the tails, right? So 0.05 is directly related to negative 1.66. In fact, negative 1.66 is the t-score, has that much area to the left of it. So these are intimately related to each other. Okay. All right, now let's run the test. Now, when you run the test, this is how it always works. I think you should get into this mode of thinking because it helps you understand what's going on a much deeper level. When you actually run the hypothesis test, make an assumption about this unknown population mean, or not, in the previous section, it was population proportion, whatever you're trying to make a claim about. So again, we don't know what this number is. We don't know what mu is. After all, someone's making a claim about it, okay? But when you run the test, you assume it's equal to whatever the null hypothesis says, just for a moment. What if it is, in this case, what if mu is 8? If it really is 8. So we're going to assume sub 0 is true. In other words, we're going to assume that mu is 8. All right, and that's, officially the first step when we run the test. Don't forget about that assumption. A lot of people ignore it. I think it's important if you just reflect on that fact. You should probably write it down just to emphasize that this is how it technically works. Okay, you're making an assumption when we run the test. We're making an assumption about what this population mean is. We're assuming it's 8. Now, based upon that assumption, what should happen when you sample 186 people from that population? Well, you should get a sample mean close to 8, right? I mean, if this is really 8, here's a population, right? I mean, huge population, everybody. If the average rating is 8, if that's what it averages to, and I randomly pick 186 people randomly from that population, then I would expect my sample mean, like when I average up the numbers from the 186 people, the ratings of the 186 people, I would expect to get a sample mean that's somewhere close to 8. Now, it may not be exactly 8 because, I've got only 186 people from the population randomly, so it's good. There might be some random fluctuation in the sample mean, but I would still expect it to be somewhere close to 8, right? if this is really 8. So this is the idea. If the population mean is really 8, which is what we're assuming when we run the test, then this sample mean should be close to 8 as well. Now, the question is, when we did this, our average, our sample mean was 7.81 from the 186 people that we surveyed. So the question is that close to 8? Is that close enough to 8 to convince you that this might be 8? And that's where this comes in, because you can look at the absolute difference between these two numbers, which is what this does initially. So we say x bar minus 8 mu, which is 8. That is telling us the difference between these two, right? It's telling us how far apart x bar is from our assumption about what the population mean is. And the absolute difference between these two numbers is what, negative 0.19. Of course, the reason it's negative just means that the sample mean is less than the population mean. If it were positive, it means the sample mean is more than the population mean. But this is how far apart they are, right? The difference between x bar and our assumption about what mu is. That doesn't really mean much to me because it's just the absolute difference. What I want to know is how far apart they are in terms of t-score, like a number of standard deviations. Okay, so that's what this bottom number does for us. The s divided by the square root of n tells us what a standard deviation is, how much constitutes a standard deviation. So let's see what that would be. That is 2.02, the sample mean, divided by the sample size, the square root of the sample size. So divided by the square root of 186. And let me just double check this because I did it off memory. The sample standard deviation was 2.02. Okay. All right, so let me see what that is on the calculator. 2.02 divided by the square root of 186 is 0.148. So every 0.148 is a standard deviation, and the difference is 0.19. So this is a little bit more than a standard deviation, right? This absolute difference. So let's see how many it is. It's a little bit more, right? That's why you divide. See how many of these 1.148 there are in 0.19. And so I'm going to divide this. I'm going to say 0.19. I mean, you can put negative in if you want, but 0.19 divided by the standard deviation. And it's 1.28 standard deviations, or t-scores in this case. And it's negative. And so that's my test statistic. Now, again, what is this telling me? This is telling me how far my sample mean is from my assumption about what the population mean is. It's a distance of 1.28 standard deviations away, which lands right here. That's my test statistic. Notice it does not fall in this critical region. Right? Remember, we call this the critical region. It did not fall in the critical region. Okay, and if the test statistic does not fall in the critical region, then you fail to reject the null hypothesis. So let's restate that. If the test statistic does not land in the critical region, We failed to reject the null. Now, why am I failing to reject the null? Because we established up front that anything more than 1.66 away in this direction, negative direction, anything more than 1.66 standard deviations away is considered too far away for us to believe. So the question is this plausible? Believe this, our assumption that mu is 8, given that our sample mean was 7.81. Is this plausible? And what we've concluded is not next to each other, but this number here is only 1.28 standard deviations away from this number here. And I need it to be more than 1.66 away because that's what I established up front as my boundary. And it did not go past 1.66. So we're not far enough away from each other. Now, this doesn't mean that I believe this is 8. It just means that if this is 8, it's reasonable to get 7.81 as a sample mean from a population where the population mean is 8. It seems plausible. So that's why I'm failing to reject this null hypothesis. It seems reasonable, plausible. The population mean could be 8, and you end up getting a sample mean of 7.81 when you sample 186 people. Does not seem crazy to us. That's why we fail to reject this assumption that mu is 8. All right, and then finally, you make a conclusion about the claim. If you're failing to reject this null hypothesis, then there is not enough evidence to support the alternative one, right? Because the top one seems like it could be a possibility. The only way you can support the alternative is to outright reject the null hypothesis. And if you outright reject the null hypothesis, then you can support the alternative hypothesis, which happens to be the claim. But in this case, that didn't happen. I was not able to reject the null hypothesis, and therefore I'm not able to support the alternative, which happens to be the claim. So in essence, there's not enough evidence to support the claim. And that's the sort of the final conclusion, right? I mean, you always address the claim as your final conclusion. You're either, supporting the claim or you're failing to, or well, there's either evidence to support the claim or there's not enough evidence to support the claim. Okay. And in this case, there's not enough evidence to support the claim. So that's the traditional method. Now, let me just mention one thing before we do the p-value method, and then I'll show you how to do this on the calculator. Suppose that for a moment, okay, I don't want to go too far off course, but suppose the average the sample mean was 6. Okay, just for a moment. Sample 186 people, and the average of those 186 people, the average rating was 6. And what would change here? This would be 6. And let's assume the sample standard deviation is still 2.02, okay? So we change this to 6. This is now 2 below our assumption that it's 8. The population mean is 8. So now you're saying -2 divided by 0.148. Every 0.148 is a standard deviation, so this is a lot. Let's see what it is. There are 13.5 standard deviations in there, right? The number 2 would be 13.5 of these 0.148s. In other words, 13.5 standard deviations. So this is -13.5 at your test statistic, and now you're definitely past the boundary, right? You're way over here. 13.5 is way past this. So you land in the critical region now. These aren't anywhere close to each other. 6 is nowhere close to 8, is what it's telling us. It's 13.5 standard deviations away from 8. So then you say, do I believe this is 8? That's the assumption that you made from the beginning. If sample mean is 6, if I randomly pick 186 people and the average rating is 6 from those people, I believe I drew that from a population that had an average rating of 8, a population mean of 8. And most people would say, statisticians would say, assumption's probably wrong. That's what's going on. This is not 8. And that's why we reject the null hypothesis. I don't believe it's 8. If this was really 8, this sample mean should have been closer to 8. 6 is nowhere close to 8. Oh, I took 186 people, which is quite a few people, right? If I'm picking 186 people from here, I should get some people that are below 8 and some people that are above 8. And this sample mean should be somewhere close to 8. It's not what happened. I got a sample mean of 6 from 186 people, which probably means this is not 8. And that's what we're saying. We're rejecting this null hypothesis. Our assumption is probably wrong. Probably what's really happening is we're drawing from a population that has a population mean of something closer to 6, and that's why the sample mean is close to 6. Regardless, we don't really know what this is. We just know it's probably not 8. That's why we're rejecting this assumption. Notice what happens here is if you reject the null hypothesis, now you are supporting the alternative hypothesis, which happens to be the claim. And so if the test statistic lands in the critical region and you reject the null hypothesis, and in this case, that means you're supporting the alternative hypothesis, which happens to be the claim. And so now you're supporting the claim. So there is enough evidence to support the claim in that case. Okay. That's if, I changed this to a 6, right? That's if this sample mean happens to be 6. Okay. So going back to the actual problem, it was 7.81, so it was 1.28, negative 1.28. All right, now let's do the value method. Okay, so in the p-value method, you don't bother finding the critical value. Okay, so you don't need to find this. Okay, so again, the p-value method, you don't find the critical value at all. So you just skip that part. Simply jump to this piece here where you run the test. And again, the first thing you do when you run the test is you assume that the null hypothesis is true. So we're going to assume that mu is 8 per second. And then find the test statistic. So you just plug everything in. Same thing we did before, right? 7.81 minus 8 divided by this, sample standard deviation, 2.02 divided by the square root of the sample size, which is 186. And you end up with the same test statistic. So that stays the same. Then, so what's different is now you locate the test statistic on this little distribution. So it's right there. And then you're going to find the area either to the left of this number or to the right of this number. And the way you know is by looking at the alternative hypothesis. And you can see in the alternative hypothesis, this is a left tail. So you're going to find the area to the left of this. Now, if this had been greater than, then you would find the area to the right of it, but it's less than, so you're going to find the area to the left of it. Okay, and whatever this area is called the p-value. Okay, so let's see if we can't figure that out. So you could do this. Remember, this is a t-distribution. So if you were to figure out that area, you're looking for area from negative infinity up to negative 1.28 on a t-distribution. So you can do that using TCDF. So go to your distribution list and go to TCDF. Lower is negative infinity, so just use negative 9999, and then the upper would be the negative 1.28, I believe. Let me see what it is. Yeah, negative 1.28, which is your test statistic. And then you have to put in the degrees of freedom. So 185. And that'll tell you the area trapped between these two t-scores, or t-distribution. It's about 0.101. That's called your p-value. Then you compare that to alpha. Remember, alpha, we're testing at a certain significance level, right? That's our alpha. And in this case, it was 0.05. And so you compare that to the significance level. So alpha was 0.05. Okay. And in this case, the p-value is greater, right? 0.1 is greater than 0.05. So the p-value is greater than the significance level, and you fail to reject the null. Which is the same thing we had under the traditional method, right? So you fail to reject the null. And again, the same result. It means there's not enough evidence to support the alternative, which means there's not enough evidence to support the claim. So there's not enough evidence, right, to support the claim in this case. So you get the same answer either way. Now, a couple other things before we wrap this up. I want to try to give you a sense of what the p-value is now that we've talked about it several times. The p-value is actually the probability. Remember, area is probability, right? Area. Anytime you find an area, a distribution, you're finding the probability. So the question is, this represents a probability, right? 0.101 is not only an area, but it's also representing some kind of probability. And so it might be good for us to reflect on what probability is it telling us. Well, here's what it's telling us. If the population mean is really 8, which is what our assumption was, right, when we run the test. So if you're drawing samples of size 186 from a population that has a mean of 8, what's the likelihood, your sample mean from those 186 people, what's the likelihood that the average rating would be 7.81? Or in other words, your sample mean would be 7.81. What's the likelihood of getting a 7.81 as your sample mean from a sample of 186 people if you're sampling from a population that has a population mean of 8? Or 7.81 or further away. And the answer is 0.1, 10% chance. That's what this tells us. So notice 7.81 right? The sample mean 7.81 corresponds to a t-score of negative 1.28. If this was a little bit lower, like when I did 6, that would correspond to a t-score that's even more negative, right? So it'd be further this way. So X bar 7.81 corresponds to negative 1.28 as a t-score, but then anything less than this, like 6, would correspond to a t-score to the left of this one, like negative 13.5, right? We found before. So this probability, 0.1, is the probability of getting 7.81 as a sample mean or smaller, because that corresponds to all these t-scores down here, right? If your t-score is over here, then that means your sample mean is less than 7.81. So let's go back over this one more time. If you sample 186 people from a population that has a mean of 8, then what's the likelihood that your sample mean will be 7.81 or smaller? The likelihood of that happening is there's a probability, a 10% chance of that happening. That's what the p-value tells you. If you turn this into a percentage, that's what this probability is. It's the probability of getting a 7.81 or less for your sample mean if you're sampling from a population that has a population mean of 8. So there's a 10% chance that this would have happened. This really is 8. This or smaller, right? And this is our predetermined number. That's what the significance level is. We say up front, anything less than a 5% chance, we consider so unlikely that that's when we're going to reject the assumption. And so if you go back and look at when I did 6, this, that corresponded to negative 13.5. The p-value for that, let's see what that is. So TCDF from negative infinity to negative 13.5 at 185 degrees of freedom, p-value for that test statistic is so small that they round it off to 0. Now, it's not actually 0. It's really, really small. I mean, I wish they had given us non-rounded number. It's probably something like 0.000001, which is like 1 in a gazillion, right? 1 in 100 million or something, 1 in a billion. Okay, so that was the case. What it's telling us is that if the population mean is really 8, the likelihood of getting a sample mean of 6 or less would be like 1 in a gazillion. That's when you would say, you know what? I don't believe this is 8, because the likelihood of getting a 6 from a population mean of has a population that has a mean of 8 is 1 in a gazillion. So it's more than likely that my assumption's wrong. This is not 8, and that's why you would reject the null. So if the p-value is less than alpha, right? So if the p-value is like, here's my p-value for this test statistic. If your p-value is less than this alpha, then you reject the null. And in this case, if you reject the null, then you're supporting the claim. And so now there is enough evidence to support the claim. Look at it. The claim is that mu is less than 8, and you're getting a sample mean of 6. So far away from 8, according to our statistical analysis, that this has to be less than 8. Right? That's the conclusion that we're making. It makes perfect sense when you really look into it. Okay, so having said all that, let me show you how you can do this on the calculator using the distribution button. So, sorry, the stat button. So if you go to stat and then scroll over to tests, this one is a one population test. So it should say, test, one population test, and it's a t-score. Now, remember the one for proportions was one prop z-test, right? The one for means, so this is a population mean, should be okay, they don't put the word mean on it. You see the z-test and the t-test. So the z-test is if you know sigma, right? Remember I showed you the first time, if you knew sigma, you get z-scores. Since we don't know sigma, we use S and it turns into a T. That's the t-test. And that's when you don't know sigma. Okay, so that's the difference. Both of these are hypothesis tests for population means. Top one is if you know sigma, and the bottom one is if you don't. Okay, so let's click on t-test and then go to stats. Now, mu sub 0, again, they label this label this here as mu sub 0. So that's 8. X bar is 7.81, the original problem. And then S, the sample standard deviation is 2.02. The sample size was 186. And then this is the alternative hypothesis. Let me go back to it. So mu is either mu is less than mu sub 0, greater than mu sub 0, or equal to mu sub 0. And mu sub 0 in this case is 8, right? That's how we're labeling 8. We're labeling it as mu sub 0. So when you see that, that's what that's referring to. So in our case, alternative hypothesis is that mu is less than 8. In other words, mu sub 0. All right, and then you calculate, and there is the t-score, the test statistic, right? We got the same thing, negative 1.28. Value is 0.101 if you round it off. That's what we got. And so you can do it either way, right? The p-value method, there's the p-value. If you use the traditional method, this is the test statistic. You would just have to find the critical value. It doesn't give you the critical value, right? Because that's dependent on the alpha. So you'd have to do that on your own. But then you can figure that out on your own. So that's how you can do it using the calculator. And one other thing I want to show you before we call it a day is, like I told you, go back to this. And let's just say I want to play with this a little bit. And I turn this into a 6 just to see what happens. You get, so X bar, a sample mean of 6 corresponds to a t-value of negative 13.5. In other words, you're 13.5 standard deviations below 8. And that value is so small that they round it to 0. Okay. Now let me try to get a more reasonable number so I can show you. It's not exactly 0 though. I want you to know that it's being rounded to 0. So maybe let's say this was 7. Okay, X bar is 7. And that would correspond to a t-score of negative 6.5. So it's 6.5, 6.75 standard deviations below 8. which gives you a p-value of 9.1. And then you notice it says e to the negative 11. This is scientific notation. Negative 11 means you have to move this decimal 11 places to the left. So it's like 0.00000000009, right, with 11 zeros in front of it, which, like I said, is something like 1 in a gazillion. That's the way you would interpret that. It's when you see this on your calculator and you have e to the negative 11, that is a really small number, right? This means you move it 11 places, the decimal 11 places to the left. That's not 9.1. It's like 0.000000091, right? So be careful about that. Regardless, that is much less than alpha, right? 0.05, and then you would reject the null. Don't believe it's 8, and the reason you don't believe it's 8 is because 7, right, is what I put in for the sample mean. 7, the sample mean is so far from 8. It's almost 7 standard deviations below 8. That's why you don't believe the population mean is 8. So you're rejecting that null hypothesis. Okay. There are some problems in the homework. I'll let you look at these, but I'll just mention it real quick. There's one problem in the homework where they give you the raw data. If you look at what it was, it's number 7. Ask a group of students to estimate the length of 1 minute without reference to a clock or watch in seconds. And then they actually timed them to see how long they said it, what it actually was. Like the first person said, stop the clock now. I think it's 1 minute, when it was actually 79 seconds instead of 60 seconds. And they did this for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 different people. And these are the numbers, the actual time periods that they waited, that they thought was a 60-second time period. So look, not giving you the sample statistics, summary statistics, they're giving you the raw data. But again, we've run into this before. Just put these numbers into L1. We'll go to stat edit. Type those numbers into L1. And then when you're done, you can go to stat. And you got two options. If you go to calc and one variable statistics, will tell you the sample standard deviation and also the sample mean, which is the two things that we need, right? In order to find this statistic, right? You need the sample mean and the sample standard deviation. So you could find those, right? You could find those by putting the raw data into L1 and then going to one variable statistics. And then I didn't put any data in, but when you go to there, you can scroll down to the mean and the standard deviation for the sample. The other option is to go to the distribution button, sorry, the stat button, go to tests, and when you scroll down to the t-test, just select data. And it will take the raw data from whatever list that you put here, presumably L1. Okay, and then make sure you put mu sub 0 in and alternative hypothesis here. Okay, so if you have the raw data, you can just do it that way. Okay, we're already 15 minutes over, so I went over last time, so I guess these take a long time though to work out. Before we end it though, does anybody have any questions about anything? Let me pull up the chat button. Okay, so I guess if nobody has any questions, we'll end it there, and then tomorrow we'll finish chapter 8. We'll talk about that last hypothesis test, which is about testing sample standard, population standard deviations and population variances. But we'll talk about that next time. Okay, I guess we'll leave it there. And just don't forget the next test is over chapter 7 and 8. Okay. All right, bye-bye. Have a good day.